Previously we learned how to use AVL trees. Okay, so when we insert a new node or when we delete one node from the tree, then sometimes the constraint might be broken. Then we have to rebalance the tree by rotating subtrees. Okay, so we know how to implement that. We talked about the specific algorithms. Okay, good. So from now on, I will introduce red-black trees and the 2-3 trees. Okay, these are another kind of binary search trees with balancing. Okay, so first one is red-black trees. Okay, it is a kind of self-balancing binary search tree. Okay, this is a kind of BST. Okay, and by definition from Wikipedia, it says the path from the root to the farthest leaf is no more than twice as long as the path from the root to the nearest leaf. So by that, I mean, the nearest leaf is in this figure is this one or this one or this one. Okay, so the path is the length is actually 3. And the farthest leaf is this one or this one or this one, and the length of path is 4. Okay, so 3 times 2 is 6. So 4 is smaller than 6. So the path to the farthest leaf is no more than twice. Okay, that's what Wikipedia says. Okay. So in this red-black trees, actually we have different colors. So black node and the red node. Okay. So with these different colors, we have a couple of different constraints. Okay, here is a set of properties of red-black trees. First one, every node is either red or black. Okay, that's one constraint. We don't have any other colors. Okay, and then the root node should be black. Okay, that's another property. And every leaf is black. Okay, so NIL in this figure, they are black. Okay, and then if a node is red, then both its children are black. It means red node cannot have red children. Okay, so in this figure, this one is red, then both children should be black. Okay, and it means, in other words, no 2 consecutive red nodes on a simple path from the root to a leaf. So it means if this one is red, then this one should be black. And if this one is red, then this one should be black. Okay, and then the last one, for each node, all paths from that node to descendant leaves contain the same number of black nodes. Okay, so I put this underline here. So from this one, we count the number of black nodes on the path to the leaf. Okay, so from here, this one is the leaf node. Okay, then actually in your slide I had some mistakes, so I just corrected the numbers. So from this node, when we check the leaf nodes, okay, then how many black nodes are there? Just one node. Okay, and if we take this path, how many black nodes do we have? 1. If we take this node, 1. This way, 1. Okay, so height is 3. 1, 2, 3. But black height means the number of black nodes on this path is just 1. So how about this one? Height is 4. 1, 2, 3, 4. Okay, and then black height is the number of black nodes 1, 2, or 1, 2, or 1, 2. So in any directions, the number of black nodes on the path to the leaf node is 2. Okay, so the same number of black nodes in all different directions to the leaf nodes. Okay, so whenever we insert or delete, okay, if any of these properties is broken, then we have to rotate. Okay, that's what red black trees are. Okay. So here's an example of insertion to red black trees. So initially, let's say this is our tree, and now we insert node 4. Okay, this one is just inserted. Again, red black trees are binary search trees. So let's say so from this subtree, this BST or these red black trees, when we insert 4, we just check the keys. Okay, so 4 is smaller than 11, so we take the left direction, and 4 is larger than 2, so we go to this node, and then the 4 is smaller than 7 and smaller than 5. Okay, then we put node 4 here. Okay, and this should be red. What if it is black? If this one is black, then 7 is uncomfortable, right? From 7, we didn't change this right subtree. Okay, we didn't change this, and from 7 to this direction, so we have only one black node, the 7 itself. But if 4 is black, then we have 2 black nodes. Okay, so that it should be red. 4 should be red. Okay, then there's another uncomfortable thing here. 4 is red and its child is red. There is a problem. So the first remedy is to change the color. Okay, so when we have a red, and this one is a leaf node, so when we have this kind of situations, we just change the color. So 5 and 8, they will be a black. Okay, then from 7, we have one black node and we have one black node, and this one is black and this one is black and this one is red. Okay, and also we have to change the color of 7. Okay, so red, black, red. Okay, perfect. Okay, but this is not it. Okay, so in this graph, node 2 is not comfortable. Okay, because node 2 is red, and the red should have a black node. Okay, so in this kind of patterns, when we have these broken patterns, then we rotate. Okay, and this one is quite similar to what we did in the ABL tree. So 7 goes up. Okay, 7 goes up, and this subtree becomes the left subtree of 7 here, and this one is here, and the 5, 4 will be, 5, 4 was the left subtree of 7, but now it will be the right subtree of 2. So we did this in the ABL trees. Okay, so quite a similar thing. Okay, now this one is better than this one. Okay, but still this is not perfect, because in this case 7 is not comfortable. Okay, 2 is comfortable because from this one we have black children, and in this direction we have the same number of black nodes. Okay, and 5 is okay. Okay, 4 is okay, but 8 is okay, but 7 is not comfortable because the left child of 7 is red, so it should not be happening, but it is happening, so we have to rotate one more time. So now we do the similar thing here. Okay, 7 goes up, and actually 11 goes down, so this subtree becomes the right subtree of 7, and 8 will be the left subtree of 11. Okay, so this one is coming from this, and 8 becomes the left subtree of 11, and 7 has 2 and 11, and we don't touch this part. And then we change the color of this one and this one. So let's check. 4 is happy, and 5, 1, they are happy, and 2 is happy, and 15, 14, 8, 11, 7, they're all happy. So we satisfy the 5 properties with this figure graph. Okay, so now we are done. So basically I told you how to rotate when we insert, when the conditions are broken, then I told you how to rotate subtrees and how to change the colors. Okay, this is how black red trees are working. Okay, then next one is 2-3 trees. Okay, in the red black trees we talked about some algorithms. Actually we didn't talk much about the algorithms. Actually I just show you some examples. When we insert one node and the condition is broken, then we had to do some things depending on the situations, depending on the pattern of the subtrees. Okay, then that is a little complicated. And now 2-3 trees, which is much more simpler than the red black trees, and it is actually even simpler than AVL trees. Okay, in the AVL trees, previously we talked about a couple of different rotations depending on the patterns. Okay, so we talked about double L rotation and double R rotations and double R, double RL rotations. And when it comes to LR rotation, there were LRA case, LRB case, LRC case. So we had how many cases do we have? 4, 5, 6, 7, 8. We had 8 cases, right? So and when we delete one node, then depending on the patterns we had a couple of different rotations. Okay, and 2-3 trees is actually a generalization of binary search tree. Okay, so it is simpler than BSD or AVL tree. Actually, BSD is not balanced tree, but 2-3 trees are balanced tree. Okay, so B trees, binary trees of order 3. So it is actually a generalization of binary search tree. And the basic idea says the internal nodes means non-leaf nodes. Okay, so non-leaf nodes can have a variable number of child nodes within some predefined range. Okay, so it is 2-3 trees. It means we can have 2 nodes or 3 nodes. Okay, and the rebalancing is not required frequently. This is the point of having 2-3 trees. Okay, so we don't actually rebalance that much. Okay, when we delete or when we insert, most of the time you don't have to change the tree structure. Okay, so insertion and deletion of 2-3 tree is simpler than AVL trees. Okay, much simpler. Okay, let's define 2-3 tree, which is a search tree that is either empty or satisfies these constraints. Okay, and each internal or non-leaf node is either a 2 node or a 3 node. Okay, so we'll talk about what 2 node is, 3 node is in the next slide. Okay, basically 2 node has 1 element and 2 children, like BST nodes. Okay, and we can have 3 nodes. Okay, 3 node has 2 elements and 3 children. So this is a generalization of binary search tree. And this is the beauty of 2-3 trees. All external nodes are at the same level. The leaf nodes are at the same level. Okay, this is kind of perfectly balanced tree. Okay, think about the BST. Okay, BST is a binary tree. Okay, and with the binary tree, even if it is perfectly balanced, even if we have a optimal algorithm to make it balanced, then still this is in the BST or in the binary tree, all the leaf nodes cannot be at the same level sometimes. Okay, if we have 3 node, then yes, all the external nodes are at the same level. So level 1, level 2. Okay, in the level 2, we have 2 leaf nodes. Perfect. But what if we have 4 nodes? then this is complete binary tree. Okay, and this is the best way to make it balanced. But still, look at this one. This one is at the level 3, and this one we have a 2 leaf nodes, this one and this one, and this one is at level 3 and this one is at level 2. This is the best that we can get. Okay, they are at a different level, but with the 2-3 trees, all the leaf nodes will be on the same level. That's the beauty, one of the beauty of these 2-3 trees. Okay, so now let's talk about 2 node and 3 nodes with figures. So with the 2 node, basically all the nodes look like this. Okay, and we can have 2 data. This is the difference from the binary search tree nodes. In the binary search tree node, we can have 1 data in the 1 node, right? Like this. This is 4, then this is 1 and 7. So we can have 1 key with 1 data in the 1 node. In 2-3 nodes, we can have 1 data and 2 data fields. Okay, so basically it's kind of the combined node with actually 2 nodes is combined. Okay, and then 2 node means we have just 1 data and we have empty node here. So this one is empty. Okay, and then if it is 2 node with 1 data, and then we have 2 pointers, and in this subtree, all the keys from this subtree are smaller than the key of this node. Okay, and all the keys from this subtree are larger than the key of this data. Okay, this is exactly the same as binary search tree node. Okay, so on the left side, all the keys are smaller, and on the right side, all the keys are larger than the node. Okay, this is good. So that's simpler. So in this case, we are kind of wasting this memory space. Okay, so we don't use that part, it's empty. But don't worry. So if it is a 3 node, so the structure looks, the structure of this node is the same as before, but in this case we have 2 data. So actually, compared to the binary search tree, actually we have 2 nodes in this 1 node. And when we have 2 data fields, then we have 3 pointers. Okay, so this one is left, and this one is middle, and this one is right. Okay, so we can have 3 subtrees. Okay, and then this one is a natural extension of 2 node or binary search tree node. Okay, in this subtree, all the keys from these subtrees are smaller than data L. This one is L, standing for left, and R for right. Okay, so all the keys from this subtree are smaller than the key of this one. Okay, and then how about this one? All the keys from this subtree are larger than data L and smaller than data R. Okay, so this is actually the middle one. And how about this one? This one is the right subtree. Okay, so all the keys from this subtree should be larger than data R. And we assume that data L's key is smaller than data R. Okay, so we have to make sure that left one is always smaller than right one. Okay, that's it. So we have a 2 node and 3 node. Okay, sometimes we can use 2 nodes, sometimes we can use 3 nodes. Okay. Now let's think about search operations. Okay, so we want to search this key from 2-3 trees. And first, case 1. If k is smaller than data left key, then go to the left subtree, obviously. And if k is smaller than right data R key, then it should go to the middle subtree. We have else here, so it means now k is larger than or equal to data L key, and k is smaller than data R key. Okay, And then else if k is larger than data r key, then go to the right subtree. Else means k equals to data l key or k equals to data r key. Okay, in that case we found it, then we have to return the node. So with this figure, let's try this search operations. So let's say, oh, I'm looking for 30, then what should you do? We have to check 30 is more than 40, then we should go to the left subtree, and 30 is larger than 20, and then we don't have anything here, so we have to take this middle pointer, and then we check 30 to 30, and we found it. If we are looking for 75, then 75 is larger than 40, and we don't have anything here, so we take this middle pointer, and the 75 is larger than 70, and we don't have anything here, so we have to take the middle pointer, and the 75 is smaller than 80, but 80 has nothing, so we say, oh, there is nothing, there is no target node here. Okay, so search is quite similar to BST, right? Okay, now let's try to insert a new node into 2-3 trees, and then sometimes we have to restructure the tree. Okay, so first search for the proper location of the key and add it there. Okay, so add it there, and if the node becomes a 4 node temporary, we don't have 4 node in 2-3 trees. Okay, 2 node or 3 nodes are allowed, but 4 node is not. But temporary, we can say, oh, we have 4 node. Then the node is split into two nodes, and then the middle key should move up to the parent. So we cannot have 4 node. Okay, so this sounds complicated, but believe me, this is much simpler than the AVL tree. In the AVL tree, we insert, and then instead of having just one line, we have to rotate the subtrees depending on different cases. Okay, so it was complicated, but in this case we have just one line, that's it. Okay, let me explain how to insert a new node. So with this example, so insert into 2 node, then just insert. Sometimes we have to shift some elements. Okay, so let me explain what it means. So given this tree, okay, we have 2 node and 3 node and 2 node. By the way, we can have a 2 node and 3 nodes at the same time in a 2-3 trees. Okay, then let's try to insert 70. So 70 is larger than 40, and then we don't have anything here, so we can take this pointer, and now we compare 70 and 80. Now 70 is smaller than 80, but this is the leaf node, and 80 is larger than 70, so we have to shift 80 to the right cell, and we have to put 70 here. So this is what we have. That's what this line means. Shifting some elements can be necessary. We just shifted 80 here. Okay, so when we insert a node, one data into 2 node, it's simple. Just insert it. Sometimes we need to shift, but still it's simple, right? So there is no problem. We don't change the structure at all. Now we want to insert a new node here, but in this case, this one is going to a 3 node. Okay, so given this one is from the previous slide. Okay, and we want to insert 30. Okay, and 30 is smaller than 40. Okay, then, and this one is now a leaf node, and we go to the left subtree, and then this is the leaf node. Okay, then we want to insert 30 here. Okay, 30. Now this is 4 node temporarily, and we don't accept 4 node in 2-3 trees, and then we have to deal with these situations. And this line says, If the node becomes a 4 node, then the node is split into two nodes, and the middle key is going up to the parent. Okay, then in this case, we split this one into two nodes, and then middle one goes up. So middle one is 20 goes up. So when 20 goes up, then 40 should be shifted, and we have 20 and 40, and we have 10 and 30. So we have two nodes here, and the middle one is in the parent node, and this node is in the left subtree, and the 30 makes the middle subtree, and this one is right subtree. Again, in the previous figure, 70, 80, they are in the middle subtrees, okay? But now we move 20 into the parent, and now parent, this one is 3 node. Originally it was 2 node, now this one is 3 node, and this one is the rightmost subtrees here, and this one will be the right subtree. And since we are splitting this one into two nodes, then this one is left subtree and this one is middle subtree. Okay, this is it. When we insert, and if we break the conditions like this, so temporarily it is making 4 node, so it is kind of breaking the rule, then we can adjust the structure. Okay, it's quite simple compared to the AVL trees. Okay, now let's try a little more complicated situations. Okay, so given this figure, given these 2-3 trees, then we want to insert 60. Okay, let's try. So 60 is larger than 40, then we take this right subtree pointer, and then this is the leaf node, and 60 goes into this node. Okay, 60. And again, temporarily, this is 4 node. Okay, then that's illegal. Then we have to deal with it. Then how? We split. Okay, we split this one into two nodes, and 60 and 80, and then 70 goes up. Okay, then now this is a little complicated. So we have 10, 30, and 60 and 80, right? And 70 goes up. So we have four pointers temporarily. Okay, this is not it. Temporarily, we have 4 nodes here. Okay, in the first stage, we had a 4 node here, but we just split this 4 node into two nodes. So now we have two nodes here, and the middle one goes up. So now this one is 4 nodes. Okay, still this is breaking the rule. Okay, then what should we do? We apply the same rule here. We split this one into two nodes. So 20 and 70, and the middle one goes up. We have nothing, but we can make new node here. Okay, then 40 can have left pointer and the middle pointer. Okay, and then 20 can have left pointer and the middle pointer. Okay, and then 70 can have left pointer and the middle pointer. That's how we get this tree. Okay, so we apply the same rule again and again recursively. Okay, so when we have a new key, then find the perfect location first and then add it. And if that makes a 4 node there, then split it and move the middle one into the parent node. Okay, then the leaf node level is fine, but in the parent node level, probably maybe we might have 4 node problem again. Then we split and move the middle one to the parent node. Okay, we keep doing this until this is 2-3 trees without 4 node. Okay, so this is much simpler than AVL trees, right? Much simpler. Okay, so to explain these three trees with different examples, I got this one from Wikipedia. Okay, these figures explained all different cases. First, we want to insert new node into a 2 node. So this is original tree, and then we insert 4. So 4 is smaller than 5, and the 4 is larger than 2. So 4 is here. And we insert new key into a 2 node, then it's just simple. That's it. But when we insert a new one into a 3 node, okay, this one is initial. And when we insert 10 is here. And it is making a 4 node temporarily, okay? Then we have to split. So 6 and 10 will stay here at this layer, and the 9 should go up, okay? And then we have 3 node here, and 2, 4, that one is here, and then we just split. So 6 and 10 is making two nodes, okay? And then when we insert a node into a 3 node, then it's a little more complicated. We already explained this one with the previous slide, but let me repeat that with a different example here. So we insert 1 into this one. Okay, then 1 is more than 5, and 1 is more than 2, so we have 1 here. Okay, good. So temporarily we have 4 nodes. Then what should we do? We split. So we split 1 and 4 will make two nodes, and then this one should go up. And this parent node is a 4 node again. Okay, so temporarily it has 4 pointers, but actually we don't have 4 pointers, but we have to implement these algorithms in this way. So temporarily it has 4 pointers, and then we split this one. So now we have a 2 and 9 at this layer, and then 5 should go up. So 5 is here. So we increase the depth of this tree only in this case. So look at this one. Only in this case we increase the height of the tree. So in this case we don't change the structure at all. In this case we have one more node in this layer, and we don't change the height of the tree. So basically, even with these insertions, the search time would be the same as before. We didn't change the length, the depth of this tree. Okay, and search time depends on the height of the tree, and we didn't change it. Only when necessary we increase the height. Okay, so once we increase the height here, look at this one. This one is 2 node, 2 node, 2 node, 2 node, 2 node, 2 node. So in this case, when we insert new node, for a while, we don't have to change the structure at all. Okay, so it's quite simple. Now let's talk about deletions. Okay, deletion is also simple compared to the AVL trees. So we have 3 node, and 3 node, and 2 node, and 3 node. And we delete 90. Basically, when we delete, we have to search first. Where is the 90? Okay, so 90 is larger than 80, and we have 90. So we found it. Then we delete this one. If this one is on the left cell, and if we have something on the right cell, then we have to shift. So 95 should be here. That's it. Okay, so we didn't change the structure at all. That's quite simple. Okay, next we delete 60. Okay, so when we delete 60, actually this one is gone. Okay, then there is a rotation here, and when this one is gone, then this one is a 3 node. 3 node means we have 3 pointers, but this one is gone. That is a problem. Okay, so we rotate. So 50 is going down and 20 is going up. So now 10, 20, 50. Okay, so perfect. Okay, so we didn't change the structure. Okay, we just change the elements here. So we didn't change the structure. But by doing this, okay, then we have lots of two nodes. And two nodes means, when we insert new node, new data to this one, then for a while, we can just accept them, not change the structure. Okay, so that's good. And next, we delete 95. And when we delete this one, then this one is gone. Then this one is 3 node. 3 node is problem here, right? So 3 node means we need 3 pointers, but we don't have this pointer. So 80 goes down. Okay, so now we have this tree. Okay, next. So now in this, from this tree, we delete 50. Then this is easy, just delete it and shift 80 here. So now we have this node, okay. Then delete 10. So we delete this one. Then there's a problem. This node is 2 node, okay. 2 node means we need 2 pointers, but this one is gone. So we have only 1 child, okay. Then we don't need this one as a child. If we have 2 nodes here, like if we had 80 and 90 here, then we can rotate. But we have only 2. Then just restructure. So just 1 node is enough to represent these 2 keys. Okay. So when we delete the nodes from T2, 3 trees, then it changes the structure only when necessary. So when we insert or delete, then we don't touch the structure if not necessary. Okay, so we can save lots of time here. So 2, 3 trees are simpler than AVL trees. We don't have to worry about the rotation, and we don't have to worry about the BF, etc. But 2, 3 trees have 3 subtrees, okay? And in the computer science, we love binary, so 1 and 0. And if it is a 3, then we don't like that much. But if necessary, we can use 2, 3 trees, but binary search trees would be more popular conceptually, but in practice, 2, 3 trees are popular too. Okay, so now we are done with chapter 10. Actually, 2, 3 trees are from chapter 11, but we don't have to go through chapter 11. And the 2, 3 trees are kind of search trees, so I just put that in the chapter 10. Okay, so in chapter 10, we talked about the problem of BSD when it is not balanced. So we introduced AVL trees. So with AVL trees, after inserting or deletions, if it is not balanced, okay, after checking BF numbers, then if it is not balanced, then we have to rotate depending on the patterns. Other than that, we can use red-black trees or 2, 3 trees. Okay,